So we have one question from the chat that we're going to address first. That was, can we also apply these methods to measure uncertainty in tensile strength load cells?
I'm not sure. Am I still on? Mm-hmm. Yes. I'm not sure what is meant by tensile strength load cells. As far as the mode is concerned, everything we talked about here is equally applicable in tension, tensile, or compression. But I have a feeling that wasn't the real question.
We will go back to that one and get some clarification.
While we're waiting for that, another question has come in I could address relating to the zero offset of load cells. If you recall the sources of error that we used, none of those was the zero offset of the load cell. And that's because we always take it out. In other words, we're using the net output, not the gross output of a load cell. So anyway, a listener has wondered, well, what level of zero is tolerable in a load cell? In other words, if you overload a load cell, the failure mode typically is a zero shift, and how much shift can be tolerated? We typically say that 10% of the rated output is a tolerable shift. Can it be greater? Yes, it can be greater, but you stand in danger of some other parameters falling out of specification, for example, with temperature sensitivity. So our advice remains stay under a 10% zero shift. Is it necessary to recalibrate with a 10% zero shift? Probably not. Is it necessary to recalibrate with a greater zero shift? Probably yes. Again, it depends on various variables that may be involved. So that's a general statement. Other questions?
So we have one. What method was interface load cell calibrated at NIST?
The calibrations at NIST are dead weight calibrations. They are performed per an interface procedure. Remember, I said that calibration was a documented procedure. So we, in fact, use a documented procedure. We tell NIST how to calibrate our load cells. The calibration procedure we use is compatible with ASTM E74, but it goes beyond that in specifying additional data points, additional descending points, and our particular adapters to use in adapting to their dead weight machines.
Got another one from the field. With the application of the digital processor, the repeatability is more important. Other errors can be corrected with the calibration table. How to achieve the repeatability? How to know the repeatability is lost in the real time?
I think in the context of this question, what is referred to as repeatability is taken care of in our discussion as what I called non-reproducibility. Non-reproducibility is a broader term than repeatability. But due to the fact that it is difficult to assign errors to non-repeatability sources, for example, thread fits and flatness and concentricities. What we did at Interface to determine numbers for those parameters is look at many, many tests using different operators, using different times of the day, during different seasons of the year, taking many, many tests and comparing the variability that we get making repeated tests. So that is basically how we come up with numbers for that. And again, I'll mention the fact that we have 2 standards for each capacity. So by comparing those together, which we do periodically, we keep in control our repeatability.
So this is a question that was asked prior to the presentation. How much out from nominal is acceptable?
We just answered that one.
Okay, good. How much correction is possible? And if we use correction, is it necessary to perform a complete calibration again with the correction factors applied?
Yeah, we answered that one.
Okay. Another question is whether or not it is suitable to use a load cell sensor that has too high an error in one direction only. For example, if my errors are out in compression but acceptable in tension, and the user only uses the sensor in tension, is it acceptable to use the sensor in the customer's application?
The answer to that question depends on the magnitude, of course, and the sources of the error. It's somewhat natural for some models of load cells to have different errors in different relative errors in tension as in compression. If they're grossly different, that may indicate an injury to the load cell. And so the answer in that case might be no. But if their numbers are relatively similar, then probably it's not an issue. It would have to be looked at on a case-by-case basis. You remember the load cell that I showed you, standard 16, which was nonlinear, like minus 0.12% in tension. That was actually more like 0.03% in compression, so that would be an example of quite a wide difference, and yet it's a very stable and dependable load cell. That would be kind of an exception to the rule. Generally speaking, I would be suspicious of something that far different.
Okay, another one. When Interface calibrates their load cells per ISO 17025, do you provide measurement of uncertainty in your calibration certificate?
The answer is yes. A requirement of ISO 17025 is that the calibration uncertainty be stated. And there it is given in a single statement where we state the uncertainty. Normally it is the uncertainty for the lowest point in the calibration, but we state just one number for simplicity. So typically it would be a number like 0.04%, meaning that each of the calibration points has an uncertainty of 0.04%. For the test data that's provided.
Another one here. Do all of the force sensors from the different vendors use the same method to characterize the force sensor? Since there are so many error sources, is there single value one can use to compare the sensors from different vendors?
That would be that is, using a single number to compare load cells would be a very dangerous thing to do, because some parameters are more important for one application than for another. However, if you want to make a comparison, you have the data sheet values to rely on, including nonlinearity, hysteresis. You will find a parameter there called non-repeatability. but it's not a very useful parameter in that context because it's just a very generalized number. Creep is a good single number to use because any load cell that has low creep generally has good quality construction. So if you were to pick a single number, creep might be that number. But again, depends on your application. What's really important is the long-term stability, and you don't get that off of a data sheet. So you can take your load cell and monitor it over time. As you see that we have done with our standard load cells, that history that we have on them is priceless.
Okay, how do you calibrate your 3-axis force sensor? And then we had another question beforehand asking about torque.
Calibrating a 3-axis load cell is no different than calibrating a 1-axis load cell. You need fixtures to position the load cell in the 3 axes so that you can independently test 1 axis at a time. Typically, we would also be measuring the other axes to measure the level of crosstalk. So apply the force in 1 axis and measure the output of all axes to get not only primary result, but also the crosstalk.
Okay, I want to make sure we get this question answered that came in before. It has to do with error correction, and specifically how much correction can be applied to a sensor before it's time for a replacement. For example, we've been told that generally if a sensor is exhibiting a 0 offset of 10% or more, the sensor will probably need to be replaced.
We answered that one.
Okay, that one's been answered. So let's move on. Does Interface provide the owner of its calibration system with an uncertainty value?
The answer is that in general, no, but we provide help. The uncertainty belongs to the laboratory. So only the operator of the laboratory knows his calibration intervals, his temperature controls, and other parameters that affect the uncertainty. So we give some help as provided in this webinar, but no, we do not give a guaranteed number.
So we had a question regarding the 3-axis again. Is there a processor in it?
In the 3-axis transducer, there is not. In the 6-axis transducer, there has to be signal conditioning to get the 6 separate axes.
And still on the 3-axis, I believe, does the interface cal stand handle multi-axis load cells and report the amount of crosstalk of each channel?
Each axis would be treated independently, so it is a matter of, well, first, can the interface system measure, say, 3 channels simultaneously? And the answer is certainly yes. As for positioning the load cell for each axis, that's a matter of mechanical adapters. So yes, one can make all of the mechanical adapters he wishes to position the load cell into the axis of interest. It becomes a much more complicated load string than what you saw in this webinar.
Still on the 3-axis, is the crosstalk varying with the load level?
Crosstalk tends to be somewhat linear. In other words, if it's 1% at 1,000 pounds, it might be also 1% at 2,000 pounds. That's not perfectly good statement, but it's generally, approximately true.
Some more questions in here. Some more questions popping up in the Q&A. How do you view percent hysteresis versus nonlinearity in ascending versus descending data? In other words, do you base that percent plus the nonlinearity spec or form a straight line fit?
The answer, if I understand the question correctly, the numbers that we talk about on our data sheets and use here routinely at Interface, nonlinearity and hysteresis numbers are based on a straight line, or in other words, a terminal line. The only time we talk about a best fit line is in the parameter called static error band. That one is based on a best fit straight line.
Do the materials age, strain, harden? Does this contribute to the differences over time between gold cells / NIST and Interface?
I think the question relates to why do load cells drift over time? Well, we have many materials in the load cell. We have the basic material, which is, let's say, steel, hardened steel. It could be aluminum. We have the strain gauge, which is a nickel chromium alloy. And we have the plastic materials in the load cell, which are insulators and glue. All of these items tend to age. The net result appears to be a positive drift with time. I'm not a good enough metallurgist to tell you which of all those components is doing the drifting, or if some of them are in fact complementing each other. But yes, there is drift in the materials.
Can you speak to the influence of gravity?
Yes. You will notice that in our units of measure in the webinar, we used LBF or KLBF. The F used to distinguish between mass and force. So all of our measurements here, we're talking about force, pounds force. You only worry about gravity when you're using mass. So, for example, we send our load cell standard to NIST to be deadweight calibrated. The deadweights at NIST had to be concerned about local gravity so that they exert the correct amount of force. However, the load cell that is now calibrated in units of force no longer cares about gravity. That load cell can be used at any location on any planet. It only responds to force. It doesn't care about gravity. That's a nice thing about the comparison method of calibration.
Can a 0.05% linearity load cell be used to calibrate a 0.03% linearity load cell? Because according to your one slide, you said a 0.04 UNC could cal at a 0.02.
The nonlinearity of the standard is not going to be important in a calibration if you account for it. In other words, use the fitted curve. So again, we go back to the example that we showed here of the standard that had minus 0.12% nonlinearity. That standard is used all day long to calibrate load cells with much lower nonlinearity. Because we use the fitted curve. That's a feature of the gold standard calibration system that easily allows you to use fitted curves on your standard.